the action potential travels down the membrane towards the synaptic end bulb or synaptic knob. You can see that inside that synaptic knob or end bulb are little tiny vesicles, and they're all filled with chemicals called neurotransmitters. This synaptic end bulb is almost in contact with the next neuron that it's trying to communicate with. The site of communication between one neuron and another neuron is called a synapse. If you look at it really close up, you can see that there is a synaptic cleft here. There's a little space between the two neurons, a very tiny space called the synaptic cleft. That synaptic cleft is filled with extracellular fluid. On one side of the synaptic cleft is the presynaptic membrane, or the cell membrane of the presynaptic neuron, and the other side is the postsynaptic membrane, or the cell membrane of the postsynaptic neuron. The way that this neuron is going to be able to transmit its action potential to the next neuron is by using the neurotransmitters that are contained inside the synaptic vesicles. The electrical impulse that's been generated does not just jump from one neuron to the next in all cases. It does happen sometimes, but it doesn't happen here. In this case, we have to use something called a chemical synapse. Remember, synapse is the communication between the two neurons. A chemical synapse is when you need to use neurotransmitters to do that, which are chemicals. So here's what happens. The action potential travels down to the synaptic end bulb on the axon. When it reaches the end of the synaptic end bulb, that membrane has in it calcium ion channels that are voltage gated. When the action potential reaches the voltage gated calcium ion channels, they open in response to that change in membrane potential. Calcium is in higher concentration outside than it is inside. Therefore, through simple diffusion, when you open up those channels, calcium ions rush into the cell. Calcium ions stimulate the breaking open of the synaptic vesicles into the synaptic cleft. This is called exocytosis. It's a form of vesicle transport. Calcium ions stimulate the exocytosis of neurotransmitters. The neurotransmitters go into the synaptic cleft, they travel across the extracellular fluid, and they come in contact with receptors on the postsynaptic membrane. These receptors are ligand-gated ion channels. They are opened in response to the presence of a specific chemical, and that specific chemical, in this case, is the neurotransmitter. In this particular example, it's acetylcholine. The neurotransmitter stimulates the ion channel, opens it up, and allows ions to either enter or leave the cell depending on their concentration gradients. If enough sodium ion channels enter the cell, you'll depolarize the postsynaptic membrane with a graded potential, just like we had when we started. So ultimately, what you're trying to do here with this chemical synapse is to create a graded potential in the postsynaptic membrane. That graded potential might be enough to go all the way to threshold and create a new action potential, but it also might not. That graded potential might only be enough, because remember, graded potentials are variable, to slightly depolarize the membrane and just get it excited. Bring it closer to threshold, but not quite enough to stimulate another nerve impulse. That's called an excitatory postsynaptic potential, an EPSP. It might actually be a situation where potassium ions are allowed to leave, hyperpolarizing the membrane, making it more negative, making it less likely to carry on the nerve impulse, which is perfectly normal. Sometimes the goal of a neuron is to stop another neuron from firing an action potential. It's called inhibition. That result is called an IPSP. You've made the membrane potential more negative by opening up potassium ion channels and inhibited it from generating an action potential. That's called an inhibitory postsynaptic potential, or an IPSP. If the EPSP is big enough, it will go all the way to threshold and generate an action potential, just like we saw before. So there are three possible results from a chemical synapse. You can excite the membrane, but not enough for an action potential. That's called an EPSP, or an excitatory postsynaptic potential. You can inhibit the postsynaptic potential by making it more negative, hyperpolarizing it. That's called an IPSP. Or you can depolarize the membrane to threshold and result in an action potential and continue the nerve impulse to the next level. Those are your three possible choices from a chemical synapse. Sometimes you can get to the nerve impulse, but it takes more than one EPSP to do that. Sometimes you can have one EPSP after another in succession, stimulating the postsynaptic membrane. And when they are added together, they can reach threshold to generate a nerve impulse. In this case, instead of using one EPSP, you're using the sum of multiple EPSPs building on the previous one, and that's called temporal summation. The sum of EPSPs over time results in an action potential. Or you can have multiple presynaptic membranes all stimulating the same postsynaptic membrane. So you have multiple EPSPs at the same time depolarizing the postsynaptic membrane. And that might be enough to reach threshold and create an action potential. In that situation, it's called spatial summation. The sum of EPSPs at the same time, all in the same space. That's spatial summation. So this is generally the idea, the basic idea of the nervous system. This is the most basic concept of the nervous system, and everything from this point out in the nervous system is built on the concept of the nerve impulse. This is how our nervous system communicates with itself from neuron to neuron, and this is how our nervous system communicates with other cells like muscle cells and gland cells. The message is always the same. Every single action potential goes all the way up to plus 30 and comes back down. Every single action potential starts at minus 55. They all look exactly the same. Action potentials are all or nothing. There are no big action potentials. There are no small action potentials. The message that the nervous system sends is always the same. The difference is the messenger. The brain knows what kind of sensation is happening to you because of which neurons are bringing that message to it. The message is always the same. But the messengers, the sensory receptors, the sensory neurons, the motor neurons, they are the difference.